All space exploration missions come from some sort of magnificent aura of passion, hope, and curiosity. They consist of individuals who push all kinds of barriers, whether in space or right here on Earth. For a mission as special as bringing the first humans to Mars, our team wanted to dedicate our name to Mae Jemison, who was the first in many aspects. She was born in 1956, a time when racial segregation and injustice was vibrant. Despite the overwhelming societal obstacles, she became a member of NASA, aboard the Space Shuttle Endeavour, and launched in 1992. She was the first Black woman to reach space. For marginalized people like myself and many others, she became more than just an inspiration. She was proof that we can ascend beyond the structures that hold us down. As such, her acronym fits perfectly with our mission. Mars Ascent Expedition, Mae Jemison Crew Ascent Vehicle, JCAV. Featured as decal on our vehicle, Dr. Jemison once said, "Never be limited by other people's limited imaginations." That is exactly what has driven us forward in designing and presenting the JCAV for you today. And for Dr. Jemison, thank you very much. The Mae Jemison VUDURU team has decided to conduct a mission around the Northeast Syrtis site, which is located at 18 degrees north and 77 degrees east near the Utopia Planitia region of Mars. Previously, our launch site coordinates were about 112 kilometers from NE Syrtis, with a total incline of 1,773 meters. In an effort to improve mission efficiency, a closer launch location was chosen. The new launch coordinates are 18.154 degrees north and 76.82 degrees east. This location was chosen because of its distance to NE Syrtis, which is 16.76 kilometers, its smaller incline of 53 meters, as well as its relative flatness. Along the path, the average annual wind speed measures about 6 meters per second, and the average maximum wind speed values can reach up to 17 meters per second.
The rover that the astronauts will use is based off of the NASA Surface Exploration Vehicle, a vehicle concept that is currently being tested. The rover wheels can pivot 360 degrees and drive 10 kilometers per hour in any direction. It houses 2 astronauts in a pressurized cabin for 14 days of living. The vehicle must also interface with the team's ingress tunnel. Being a candidate for Mars 2020 landing sites, NE Syrtis offers a few geological features that make it a scientific region of interest. The overwhelming majority of the region is filled with surface and subsurface iron and magnesium clay, which is most likely aqueous in origin. Other regions around Syrtis are scattered with layered sulfates, olivine carbonate variably banded formations, crater-retaining mafic-capping rocks, and low-calcium pyroxene-bearing mounds. The abundance of minerals at the site suggests that it is a possible location for past life. The history of the site is revealed by studying the layers of minerals, which illuminates the transition period between the Noachian and Hesperian epochs. Studying the site would reveal much about the radical changes occurring during this transitional time.
The mission depicts that the Mars Ascent vehicle will launch from Earth on April 11, 2033 on the SLS and land on the surface of Mars on December 26, 2033 at a solar longitude, or LS, of 303.5 degrees. The mission will last for 30 days, so the crew will be on Mars until a solar longitude of 320.9 degrees. This is optimal because certain regions of the northern hemisphere of Mars are the warmest during the Martian northern hemisphere winter, which occurs at an LS of 270 degrees and is just after the Martian perihelion, which is an LS of 260 degrees. The temperature will also be higher at the NE Syrtis site because it will be experiencing some of the lowest albedo values in the region. The average temperature in the region is around negative 55 degrees Celsius. The maximum temperature goes up to around 18 degrees Celsius, and the minimum temperature is around negative 125 degrees Celsius. This launch time would occur at the end of the dust storm season, which ensures temperature stability and less dust accumulation. Dust accumulation affects the amount of solar radiation received by dust by around 10 to 20%, but the dust can be removed by humans with dust removal rags, compressed air, or a vacuum.
Mars Ascent vehicle will be set to launch when the ERV reaches a true anomaly of 14.1 degrees with respect to the reference direction or apse line, which will be normal to the launch site. The MAV orbit will have an orbital inclination of 18.154 degrees and a launch azimuth of 90 degrees. This will put the MAV in the same orbital plane as the ERV, which will help to avoid extensive maneuvering. The MAV's orbit will form a 90-degree angle from its apse line to the intersectional node line between its orbital plane and the equatorial plane of Mars. The initial launch will take approximately 481 seconds to complete until orbit is achieved, and the maximum gravitational force experienced by the MAV during ascent will be 2.17 Gs. Due to the effect of Mars's rotation and the loss of gravity during ascent, as the MAV arrives in its 125-kilometer parking orbit, the net launch delta V will amount to approximately 3.81 kilometers per second. The low density of the Martian atmosphere will make drag a nearly negligible force, even during the MAV's ascent below the Kármán line up to an altitude of 80 kilometers.
So here's our specific mission profile. To start off, after doing surface operations and sample collections for most of their 1 month stay, the crew will begin launch preparations and will enter the MAV as they prepare for liftoff. The MAV will then launch into the 125-kilometer orbit, requiring a total burn of 3,754.1 meters per second. After getting into the 125 by 125-kilometer orbit, MAV will first complete one whole orbit around Mars, during which the crew will do sensor collaborations and perform checks to make sure everything in the MAV is working properly. After this, as the MAV finishes its one orbit and approaches its launch point again, the ERV should be at an angle of 2.79 degrees with respect to the MAV. At this moment, the MAV will do its first orbital burn to enter into the home and transfer orbit of 125 by 200 kilometer orbit, requiring a delta V of 19.2 meters per second. If all the launch and burn times have gone successfully so far, the MAV will then remain in this orbit for about half the orbit, and as the MAV approaches the apoapsis of the transfer orbit, the ERV should approach the periapsis of the 200 by 200 kilometer orbit. At this point, the second orbital burn will be performed at the apoapsis of the transfer orbit, which will require a delta V of 18.2 meters per second, so that the MAV can enter into the 200 kilometer orbit, leading slightly ahead of the ERV. The MAV will then have matching speeds and trajectories as the ERV, from which the MAV can then proceed to go through the process of docking, rendezvous, and docking. After consulting with engineers from NASA, we were able to conclude that the docking process should take around 3 hours. After docking has been confirmed a success, the crew will enter into the ERV after 5 hours from liftoff. This is the specific mission that the crew will follow during the time from launch until reaching the ERV.
The JCAV has two major configurations, surface and orbital. On the surface, the JCAV's primary functions are to keep itself powered and to provide a space for sample storage. To keep its batteries powered in the surface configuration, JCAV is equipped with 2 deployable solar panels along with a suite of communications in order to stay connected with the ground stations on Earth. The JCAV's other surface objective of sample storage is achieved by an innovative sample storage system that provides the crew with over half a cubic meter of compartmentalized storage space that can be accessed and filled from the Martian surface anytime during their 30-day excursion. The orbital configuration of the JCAV, while similar to the surface configuration, has a few key differences. Before launch, the surface communications and the solar panels are removed, and during the launch, the landing leg structure is left on the surface. During launch, while in orbit, the JCAV heavily relies on its innovative propulsion system. Another key element of the orbital configuration is the crew cabin, which has an inner diameter of 2.3 meters and a height of 2 meters. On top of the crew cabin features the NASA docking system, allowing for easy interfacing with the ERV in orbit. A major constraint on the minimal Mars Ascent vehicle theme was the dry mass of 5,000 kilograms and 15,000 kilogram wet mass for a total limit of 20,000 kilograms. Therefore, a considerable amount of effort was spent tracking the mass of components in the JCAV design and attempting to save or cut down on mass wherever possible. The current design of the MAV has a total dry mass of 4,136 kilograms, including crew and 100 kilograms of samples, though a much larger mass of samples is likely possible. The propulsion team has determined that the full 15,000 kilogram propellant mass will be required. This leaves the JCAV with an estimated mass of 19,136 kilograms at 17% mass margin on the dry mass. In order to save mass on team design components, finite element analysis was used to save an upwards of 500 kilograms on structural components, while still maintaining a safety factor of 2. The innovative storage system on the JCAV is designed to maximize storage flexibility and volume. To accomplish this, the storage system will be an isolated pressurized section of the JCAV, including a dedicated dust mitigation system. Functionally, the sample storage system consists of 16 hermetically sealed storage containers placed on a rotating base for one-at-a-time access. The storage system has 2 access hatches. The surface access hatch is placed under the side hatch and can be used throughout surface operations and directly filled from the Martian environment. During launch and orbital operations, the sample storage system will be pressurized and a dust filtration system will be active to mitigate any dust which may have entered the system during surface access. In orbit, the crew can access the storage system via a hatch on the floor of the crew cabin, allowing the crew to transfer the samples into the ERV if desired. A major feature of the surface configuration of the JCAV is the crew ingress tunnel. In order to enter the crew cabin, the crew will utilize an inflatable pressurized tunnel. This method of ingress keeps the crew completely isolated from the Martian environment and allows for mass savings on the JCAV because this method removes the need for a dedicated airlock system. However, the ingress tunnel assumes and is dependent on the existence of a pressurized rover able to accommodate 2 crew while also being able to interface with the ingress tunnel. As mentioned by the environmental team, current Mars mission architectures include a rover that meets these requirements needed for the JCAV.
The JCAV mission features an innovative propulsion design based on some heritage components. The MPS, or Main Propulsion System, called the MAV system, or Mars Ascent Vehicle Engine System, is a custom design fully developed with deep space missions in mind. The RCS, or Reaction Control System, is based on the R4D engine used during the Apollo missions, however modified to have a new propellant combination and a higher performance. The mission requires a total of 3,810.49 meters per second of delta V. However, the propulsion system is capable of producing over 5,091.25 meters per second of delta V at the max mass allotment of 20,000 kilograms. However, the JCAV vehicle is under 20,000 kilograms, which means our actual delta V is greater than 5,091.25 meters per second, meaning that the safety factor is actually 1.5, which is the required amount for a NASA human-rated space mission.
When deciding on propellant selection, in situ resource utilization, noted as ISRU required fuels, were heavily strayed away from due to the increased mission complexity that ISRU requires, and the Q&A session with the judges that detail that ISRU should not be relied upon unless for a very good reason. This is reflected in our star chart as shown, and through this, a non-liquid oxygen propellant combination was chosen. Comparing traditional hypergolic or storable propellants, dinitrogen tetroxide, which will be noted as N2O4, and monomethylhydrazine, noted as MMH, were looked at for their past usage in systems that had very high performance. In the modern day, pure N2O4 has been switched with a mixed oxide of nitrogen, noted as MON. This is a percentage of N2O4 mixed with a percentage of nitric oxide, which will be noted as NO. What was analyzed is 75% N2O4 and 25% NO by mass. The addition of NO allows for a significantly lower freezing temperature compared to pure N2O4. This is much more similar temperature to the freezing point of MMH, while the usage of a MON as well reduces the corrosion ability of pure N2O4.
The MAV engine was carefully designed to fulfill the propellant needs and the performance necessary to complete the rendezvous with the ERV. In addition, the MAV was restricted by the height due to the transfer tube. Each MAV will have a thrust of 20 kilonewtons. Utilizing a gas generator cycle provides a high chamber pressure of 1100 psi. In combination with an expansion ratio of 400, allows for the engine to produce a vacuum ISP of approximately 334 seconds and a ground ISP of 327 seconds. For gimbling, each engine is equipped with 2 electromechanical actuators to allow for an 8-degree range in the pitch and yaw axes for total control of the vehicle on ascent. The reaction control system, or RCS, of the MAV contains 4 thruster quads situated on each corner of the MAV, for a total of 16 RCS thrusters. This orientation provides complete control of the vehicle during orbital maneuvers and adjustments. The RCS also utilizes the same propellant as the MAV, but with a pressure-fed design. One thruster produces a max thrust of 490 newtons, and the system has an oxidizer-to-fuel ratio of 2.2 to 1.
JCAV will consist of 8 nested propellant tanks, 4 dedicated to the MPS and 4 to the RCS. The MPS tanks are evenly spaced around the MAV to optimize volume allocation while maintaining a balanced center of mass. Contained within these tanks is a helium pressurization system which will allow for controlled pressurization of the tanks during flight. The tanks are manufactured using an aluminum lithium 2195 alloy to mitigate the risk of storing hypergolic propellants in close proximity to one another due to the nested tank design. In addition, the tanks are insulated using a 2-layer system of multi-environment, multi-layer insulation, or MEMLI, developed by Quest Thermal. It is incredibly effective with a low thermal conductivity and emissivity and a heat flux of less than 1 watt per meter squared at the average surface temperature of the landing site. Specific tank parameters can be seen in the table shown. The volumes of the tanks were calculated at 25 degrees Celsius, as this is the temperature at which the propellants are loaded into the tanks on Earth. The tank sizings also account for anti-slosh, anti-vortex, and ullage requirements.
The anti-vortex baffles will prevent gases from entering the engines that could cause stalling or some other malfunction, which could lead to a critical engine failure. Without one, the flow velocity would be non-uniform along the flow path of the fuel and oxidizer and could allow vapors into the engine. The design for these baffles is a simple cross over the drain pipes within each of these tanks. The anti-slosh baffles will provide damping to the liquid propellants during the launch and flight. They are flat rings evenly spaced in each of the tanks in order to control the movement of the fluid while the vehicle is in motion. The flat ring baffles will help to maintain structural integrity and stability of JCAV during flight. Both the anti-slosh and anti-vortex baffles will be constructed out of an aluminum alloy similar to the material of the body of the tanks.
The landing site temperature averages negative 55 degrees Celsius. However, MON 25 has a crystallization concern just below negative 40 degrees Celsius and a propellant freezing point just below negative 50 degrees Celsius. Additionally, MMH has complications with its variation in viscosity at low temperatures. This can be solved with an aforementioned passive insulation system and an active heating system, which keeps the temperature of both propellants at 0 degrees Celsius. To maintain the 0 degrees Celsius fuel temperature, an active heating system is necessary alongside the insulation. The heaters chosen are all polyamide etch foil patch heaters on the aluminum lithium tank exterior just below the insulation, with a single aluminum side to increase heat spread. The selected patch heaters are an innovative alternative to classically used Kapton film patch heaters, due to their abilities to provide higher wattage per surface area and to operate at very low temperatures with little degradation or loss of performance. Each heater will provide a maximum of 1 watt per centimeter squared of heat, which is a value corrected from the technical paper, and heaters in our system will be arranged in 2 different ways for MPS tanks and RCS tanks due to the differences in volume and surface areas. Furthermore, to ensure functionality, every other heater in a loop will not be utilized except in the case of failures and significant loss in resistance, which is highly unlikely as the heaters are not put under significant stress. The heaters will use a computerized system based on thermocouples within the tank to determine when they should be activated and how many should be activated to ensure efficient use of resources.
During the launch profile of the JCAV vehicle's mission, the astronauts will feel a maximum of 2.64 Gs. The mass reduction will be 30.57 kilograms per second during the MAV burn, 0.62 kilograms per second during the RCS burn, and the maximum velocity will be 5,146 meters per second.
With a relatively short mission duration, many extensive human factors considerations can be avoided with the reference to NASA STD 3001. This includes extensive waste treatment systems and large stores of provisions. The MAV will support a crew of 2. Both astronauts will wear an IVA suit and will use maximum absorbency garments, MAGs, during the mission. The traditional seating arrangement allows the G-load to go through the crew's chest and minimize the effects of the launch. In accordance with NASA's STD 3001, there is a 1-day supply of food and water, first aid, and hygiene kits for the crew. Items such as no-rinse toiletries, including shampoo and body wash, deodorant, and dental care are included. Beyond the required consumables, there are several inner cabin systems that need to be considered for the crew's safety. The respiration system stems from a single nitrogen gas tank and oxygen gas tank that will provide 1.5 days of breathing for the crew at 1 atmosphere of pressure. Dust mitigation will be performed by a filtration system, and crew members will be required to change into an IVA suits before boarding in order to further reduce this risk. An optimized absorption system of lithium hydroxide is utilized to remove carbon dioxide and other similar toxins. Finally, a smoke detection network can identify multiple fire signatures and other hazardous gases. The cabin will be equipped with a fire elimination system consisting of water-based foam to combat onboard fire.
Keeping the cabin at a comfortable temperature of 21 degrees Celsius is crucial to ensuring the well-being, satisfaction, and vitality of the crew. This will be performed by both active and passive methods. The active heating system utilizes heating patches that are attached to the cabin wall, which will provide primary heating. Meanwhile, the passive system of multi-layered insulation provides insulation as well as protection from external radiation. Excess heat will be removed from the cabin by a dual-loop system. Heat will be transferred to the environment from the cabin by a series of tubes in the wall using both water and alcohol. Fans circulating the cabin air will also provide some temperature stabilization as well as air circulation. It is important to note that most of the life support and cabin essential systems mentioned are optimized versions of the ones found on the International Space Station and Space Shuttle missions.
The electrical power for JCAV is sourced from 2 solar arrays featuring gallium arsenide triple junction technology, utilized in both the InSight lander and Orion multi-purpose crew vehicle, with each circular array producing upwards of 1,300 watts and the average sol having 12 to 13 hours of sunlight. Approximately 31.75 kilowatt hours per sol are generated. Only 63% of such will ever be used, leaving 37% in excess power to accommodate for any added inefficiencies in generation, such as dust accumulation. Energy is stored in 5 120-volt 55 amp-hour batteries, totaling 33 kilowatt hours stored. These lithium-ion batteries use similar cells designed for Orion and are produced by Eagle Pitcher, who feature an expansive space heritage. The JCAV will alternatingly draw from 2 of the 4 main batteries, with the 5th as a redundant backup while on the Martian surface. For launch and orbital operations, only 3 batteries will be needed at maximum. The Power Management and Diversified Bus Unit, PMDBU, will regulate and distribute power at the 4 traditional voltage buses of 5, 28, 52, and 120 volts, as well as any other specified lines needed. The PMDBU includes current voltage IV sensing, as well as circuit protections to ensure as smooth operations as possible. JCAV's power consumption can be broken down into 5 modes: daytime surface operations, nighttime or sleep surface operations, and the 3 orbital rendezvous attempts. The power budget shown has been slightly adjusted from the technical paper to correct marginal wattage misrepresentations. With all modes accounted for, consumption will never exceed more than approximately 20,000 watt hours, leaving 37% in excess as mentioned previously. While crew cabin elements consume the most in both surface and orbital operations, it should be noted that there is a built-in 10 to 15% margin for that budget specifically. All of JCAV's functions are controlled by a modified FMZ 2000 flight management system from Honeywell. The crew will utilize a glass cockpit of 3 touchscreens with physical switches for critical functions only. A glass cockpit was chosen for the assumed heritage it will have from being used on Orion, as well as to minimize system mass and wiring complexity. This will be backed up by 2 identical computers and 3 redundant touchscreens on an isolated bus from the main. Since the flight computer and user interface are based on Orion system, this ensures reliability and reduces the unique training needed to fly the JCAV. On the Martian surface, JCAV will have 3 antennas for as many communication methods. The ultra-high frequency UHF antenna, which is also used on Perseverance, will transmit and receive data utilizing the Mars Reconnaissance Orbiter, MRO, as part of the Mars Relay Network. The MRO will then in turn transmit the JCAV data back to the Deep Space Network, DSN, on Earth. MAVEN will be used as a backup relay. The Vehicle Orbiter Relay Link features rates of up to 2 megabytes per second. The steerable Ka-band high-gain antenna stems from a patent-pending dual-frequency
right-hand circularly polarized RHCP HGA design for the proposed Europa lander. It will perform direct-to-Earth link communication between the JCAV and the DSN. There is also a Ka-band low-gain antenna, LGA, which plays a similar role to Perseverance's X-band LGA, being a rugged link for receiving direct data and commands from the DSN. It should be noted that the Ka-band is 4 times higher in frequency than the X-band, currently being used on most Martian vehicles, and thus enables improved transmission rates. For launch and in-orbit communications, the JCAV relies on high-far Ball Aerospace conformal S-band phased array antennas, PAAs, similar to the ones being used on Orion. They will perform direct-to-Earth link communications. Since aging Mars relay satellites are of concern to some, JCAV also features an experimental modular agile scalable optical terminal, or MASCOT, which will aim to demonstrate either optical relay communications with a future orbiter or direct communications downlink to Earth.
In regards to the TRLs, or technology readiness levels of the JCAV vehicle, there is a wide array of values. This is due to some subsystems being fully fleshed out components that already exist and have been flight proven, and some that need to be completely custom built from the ground up. These current TRL values will be increased over the time that the mission development occurs, and by the time the mission is go for launch, all the TRLs will be high enough to be used during a human-rated space mission. In order to ensure this, the team has decided to structure their timeline to support the lowest TRL items first and the highest TRL items last. As evidenced by the JCAV mission timeline, the lowest TRL items are actually the first to be developed, matured, and tested before the team shifts any focus to the higher TRL items. The timeline also incorporates the rigorous NASA reviews that are required to ensure that the mission is progressing safely and that the development timeline is still reasonable for the mission date. The JCAV mission features many commercial partners who have either already demonstrated technology, are in the process of demonstrating technology, or will demonstrate technology that will fit the needs of the JCAV mission and ensure the completeness and successfulness of the mission. These companies include Agile Space Industries, Eagle Pitcher Technologies, Ball Aerospace, HiFAR Incorporated, L3 Harris Technologies, General Dynamics, Lockheed Martin, Quest Thermal, Honeywell Aerospace, Solero, and Northrop Grumman. The JCAV mission not only features the use of commercial partners, but also features the use of NASA facilities in order to develop, test, and launch the vehicle to the site on Mars. These facilities include the Johnson Space Center, the Marshall Space Flight Center, the Goddard Space Flight Center, the Jet Propulsion Laboratory, the Glenn Research Center, the Langley Research Center, the Armstrong Flight Research Center, and the Kennedy Space Center. As seen by the locations of the commercial and NASA facilities, the JCAV mission will incorporate a nationwide workforce who will work together to develop, build, test, and manage the mission during all phases of the mission, including launch, arrival, landing, on-surface operations, and the ascent phase. The JCAV mission's total cost estimate is $11.8 billion. This is given in 2033 dollars using a constant inflation rate of 2.5% from 2021 till 2033 based on the current US inflation trends. This estimate is also given using a range of +15 -10 due to the young status of the proposal. This range is between $10.6 billion to $13.6 billion. These values are well underneath the provided funding of $18 billion and allows the team plenty of room in case any unexpected costs do arise during the development, testing, or actual mission phases to allow the team to continue the mission. Finally, the JCAV team would like to present the risk matrix associated with the mission. The risk matrix features a likelihood consequence table, which features the risks that in this current stage of development pose the largest threat to the overall success of the mission. However, during the design and development phases, implementation of these risk mitigation strategies, such as providing healthy margins, implementing redundant systems and fail-safes, as well as implementing strategies learned through future crewed space missions, such as the Artemis missions, there will be a very small chance that any of these risks will actually end up posing a significant threat to the overall success of the mission. The JCAV team would like to thank you for taking the time to listen to this presentation, and we would now like to open up the floor to the judges for the Q&A session. Thank you.